In the last video, we started looking at electric fields due to continuous charge distributions for the case of linear charge distributions. Here, we're going to do another sequence of examples. We will start first with a ring of charge along its symmetry axis, extend that to a disk of charge along its symmetry axis, and then finally extend that to an infinite sheet of charge. So the procedure is the same. You go ahead and you identify some small chunk of differential charge, and you start thinking about where the differential contribution of the electric field is going to point, and also think about what variable you ultimately want to end up integrating over. So I'll go ahead and mark out here first a differential chunk of charge, dq. Let me just highlight that out like that, and we'll just label that dq like that. Now this takes up a chunk of arc length, ds. So we can do the same game we were doing before with linear charge density. We can say that the linear charge density would have to be equal to the ratio of dq to ds, but that would also be equal to the ratio of the charge over the whole thing divided by its circumference. So this would be q over 2 pi r. Now, ultimately, though, we want to think, is even ds a good choice of integrating variable? And when you're looking ahead to integrating, you're thinking, nah, I think what's going to be good is if we go ahead and integrate over some angle theta. So let's go ahead and do that. So we can mark out this angle right here and say this is d theta. So our next step is what we've got so far is we've got dq is equal to q over 2 pi r ds. Now we want to express this ds in terms of this d theta, which we can totally do. It's equal to r it's equal to r d theta by the definition of arc length. So then this becomes q over 2 pi r times r d theta, and so we are left with our dq being equal to q over 2 pi d theta. Awesome. So now that we have identified that, we want to go ahead and start figuring out its contribution to the electric field. So again, same deal. If we assume the charge is positive, the contribution to the electric field it makes, dE, will point off like this. And again, you can look at this and say, oh, you know what? For every piece I've got like here, there's a matching piece over here that would cancel out what was happening in x and y. And so again, we've already worked out that the direction of the electric field is going to be straight up. So this is my E there. All right, so again, it's going to be the same game. I recognize that the electric field will be equal to the z component of the electric field. So all I need to add up are the z components due to each of these differential contributions. So let's go ahead and start with that. It'll be helpful if we mark this angle. Let's call it phi here, since I've already used up theta. And we will go ahead and come up with an expression first for DE and then for DEZ. All right. Well, DE, will be equal to K, or 1 over 4 pi epsilon naught, dq over this distance right here squared. Well, this distance right here is the square root of r squared plus z squared. So this will be root r squared plus z squared squared, or 1 over 4 pi epsilon naught dq, over r squared plus z squared. Next, we're going to want to take the z component of this. So we can say that DEZ is equal to DE times, and looking at our angle phi here, the z component of E is going to be this piece right here. And that is going to be an adjacent, so that'll be cosine phi. And again, we're going to play the same game where we can use the physical triangle here to work out what cosine phi is. So cosine, remember, is adjacent, which is z over the hypotenuse, that square root. So this will be dE times z over the square root of r squared plus, over the square root of r squared plus z squared. All right, so substituting in our dE, we get that DEZ will be equal to 1 over 4 pi epsilon naught dq, it'll just leave the dq sit there, times z over r squared plus z squared. Sorry about that. R squared plus z squared to the 3/2 power. All right, so all that remains is to substitute in our dq. Is ultimately we want to integrate over this angle theta right here. So we'll put in the dq is q over 2 pi d theta. There we go. And now, now the whole game is going to be to realize that E is equal to EZ. So now we can just integrate DEZ. So okay, when we put in DEZ, let's go ahead and pull out everything that does not depend on theta. Oh wait, that's everything. So, sorry, I dropped an epsilon naught there. So that'll be 1 over 4 pi epsilon naught q over 2 pi z over r squared plus z squared to the 3/2 power, integrating d theta. That's the only thing we're integrating over. And since we're integrating over the whole circle, we integrate from 0 to 2 pi. So again, this is an integral you can look up in a table, and you will get that this integral is equal, when you evaluate the limits, is equal to 2 pi. So that 2 pi will cancel off against that 2 pi there. And so we are left with the electric field being equal to 1 over 4 pi epsilon naught qz over r squared plus z squared to the 3/2 power. And again, we should check units, and I will assure you that when you check units, they do work. And the other thing that we should do, though, is check the limiting cases. So the two limiting cases that we can think of that we understand right away is if z is equal to 0, we know that all the differential contributions to the electric field will be in the plane, which means that there won't be any z components, so we should get 0. So if I put in z equals 0, okay, 0 here, that's a 0 in the numerator, 0 there, that's something that's not 0 in the denominator, 0 over not 0 is 0. So yes, we get the electric field is 0 if we are right at z equals 0. The other case we can think about again is if z is big compared to r. If z is big compared to r, again, this object is going to look like a point charge, and so we would hope to see something that looks like kq over z squared. So let's see if that's true. So if z is big compared to r, then right here we'll have r squared plus z squared, and if r is small compared to z, r squared is really small compared to z squared, so we can make that go away. You have z squared to the 3/2, which is z cubed, is z over z cubed is z squared. So yeah, the units check, or so the limiting case checks. When we are far away from the ring of charge, we recover the point charge. All right. So something that physicists like to do as much as possible is see if they can recycle results. Usually we try to be cute about and say we're doing we're extending the work. And the logical extension here is to think about a disk of charge. And again, this will be along the symmetry axis. There we go. We'll try that. Yeah, okay. So let's go, for clarity's sake, I think it'll be a little easier if I do my disk more. Yeah, that's a bad disk. Let's try it again. There. All right. So now the idea is if I'm sitting out along the symmetry axis of my disk, so this is now a disk, and you know it is because I wrote a label saying it is a disk. And I'm trying to draw in perspective. Okay. So let's say again you are some distance z out from the symmetry axis of the disk. What you realize after a quick moment's reflection is, you know what? I can think of the disk as a collection of rings of charge. And I already just worked out the ring of charge. Let's do that to just help make that a little clearer. So what I can do is if I make my rings of differential if I make these rings of differential thickness, then that is the case we were just looking at in the limit of it being differentially thick. So again, we'll say that the radius of this is big R. We'll say it holds charge Q. So now we're going to need to do a surface. Ultimately here, what we're going to integrate over is the radius. So we would like to get an expression dq in terms of dr. And we'll start by looking at the surface charge density. We know that we have sitting on this ring right here some differential charge dq. And so this will be equal to dq over the differential area of this ring. And we'll have to be a little careful about that, but we'll get there. This will be equal to the charge of the whole thing over the area of the whole thing. Well, there are a couple of different ways you can go about getting what this dA is equal to. One way you can do is just say, hey, if a is pi r squared, then taking the formal derivative, the total derivative gives us that this is 2 pi r dr. Sorry, this should be little r because the radius of my ring is little r. Oops. Just do it like this. Come on. So yeah, we'll say that this distance here is little r. That's the thing we'll integrate over. So then the area of this circle is pi r squared. So then dA, if we take the total derivative, is 2 pi r dr. If you don't like that, a more heuristic way to think about it is thinking about unrolling this ring. And so we can do that. And if you unroll that ring, what's its length going to be? It's going to be 2 pi r, and its height is dr. Then you say, wait a minute, shouldn't we have like tiny little darts right here? Yes, but in the limit of this thing going differential, those darts go away. So that's another way you can do it. And you can look and say, okay, base times height is 2 pi r dr, and we're good. Either way. So that's what we're going to put in, though, for our dA is 2 pi r dr. So we get that dq over 2 pi r dr is equal to q over pi r squared. So we get that. Actually, you know, I'm going to leave this as eta. That'll be more useful looking ahead to a future result. Sorry about that. So we'll just say this is equal to eta, and then we'll rearrange this to say dq is equal to 2 pi eta r dr. Okay, so we've got our expression for dr, and now the whole trick is that this ring here is giving me a differential contribution to the electric field pointing this way. And every single ring, because we're on the symmetry center, and we've already figured out that you'll either point straight toward or away from a ring, we know that all our DEs are going to be pointing the same way, and so they're just going to pile up, and we get that our total E is going to point the same way. So we can go ahead and start setting up the integral. And we will be recycling this result here, except we just use a dq for it. So let's go ahead and, whoops, sorry about that. We will steal this and dress it around. All right, stolen. And now what we want is we want the differential contribution due to our differential, our differential charge dq. Alrighty. So then we can go ahead and say E will be the integral, and then we'll put in that dq is this. So this becomes 1 over 4 pi epsilon naught. dq is 2 pi eta r dr over r squared plus z squared to the 3/2 power. Okay. So one small favor is we can cancel the 2 pi here, be left with a 2 there. And now to get E, we're just going to integrate our dE. So we can pull out whatever constants we still have. Let's see, we've got an eta over 2 epsilon naught. And we are going to be integrating with respect to r. Well, actually we can, yeah, integrating, sorry, this should be a little r right here. My apologies. And the reason this should be a little r is because it's the radius of the current ring we are integrating. There we go. So we are integrating with respect to r, r over r squared plus z squared to the 3/2 power. And our limits of integration will be 0 to big R, the radius of the disk. All right. So again, this is something that you can look up in a table. And when you look it up and you make the substitutions, you will get that the electric field strength is eta over 2 epsilon naught times 1 minus z over square root of z squared plus r squared. All right. So this one's a little rough. We should be asking ourselves again, does this make some sort of sense in limiting cases? And at least for the case of when we're far away, we should be expecting it to look like a point charge. So again, let's see if that's the case. You can convince yourself that for the case of z equals 0, where you should get 0 because of symmetry, you're going to have to do some L'Hopital rules action, but this is going to evaluate to 1 when you take the limit and you get 0. But now let's look at the limiting case. Of z much bigger than r. Once again, we expect this to look like a point charge. And so let's see if we actually get that. The trick we're going to do here to cope with this square root is we're going to use a thing called the binomial expansion. So we're going to get that E is equal to eta over 2 epsilon naught. We're going to have 1 minus. And then if you remember from calc, binomial expansion is if you get something that looks to the form 1 plus x raised to the n power, where x is much less than 1, we can approximate that with just the first two terms of the Maclaurin expansion for it. Sorry, Taylor expansion. No, Maclaurin. And approximate is 1 plus nx. All right. And this is if x is much less than 1. So if I'm going to do this, I need to get this into a form of 1 plus nx. My x here is a z squared. So what I can do is I can write this in a form of z over the square root of, and since the thing I want to be my, so we can write this as z squared times 1 plus r squared over z squared inside the root. All right, so we can pull z squared outside of the root to give me a z, which cancels that z there. So I'm now left with eta over 2 epsilon naught times 1 minus 1 over the square root of 1 plus r squared over z squared. So r squared over z squared is definitely less than 1 because r is a lot less than z. So this is a good candidate for my binomial expansion. So we can say that this is approximately eta over 2 epsilon naught times 1 minus, and then to get it even more into our binomial expansion form, we'll say 1 plus r squared over z squared to the negative 1/2 power. And sorry, that's not approximate, that still equals. And now applying the binomial expansion, we can say that this is approximately eta over 2 epsilon naught times 1 minus. All right, so our expansion is going to be 1 plus, our n is negative 1/2, and our x is r squared over z squared. All right, so there. So 1 minus that 1 will cancel, 1 minus, and then minus a minus a half gives me a half. So this becomes eta over 4 epsilon naught r squared over z squared. Now, what we got to do is put back in that eta was q over pi r squared. So let's do that. So we end up with q over 4 pi epsilon naught r squared over r squared z squared. And this finally equals 1 over 4 pi epsilon naught q over z squared. And that checks, and we recover our point charge. All right, so the limiting case works. But now here, what might be more interesting is that there's still another limit we can do. We can think about a plane of charge. And of course, this is going to be an infinite plane of charge. So if I have an infinite plane of charge, like so, what I know is no matter where I am, if I draw electric field lines, since the electric field lines can't cross, the strength of the electric field can never change. And since it doesn't matter where I am, since with an infinite plane of charge, I can't tell where I am with respect to the plane, the electric field has to look the same everywhere. So we should expect the electric field to be a constant. So, okay, but one way we can think about this is to say we can imagine this as being a disk of charge where we just let the radius of the disk go to infinity. So we can go ahead and one more time steal our disk of charge result. There we go. Which said that E was equal to eta over 2 epsilon naught, 1 plus Z over Z squared plus R squared. And then what we'll do is we'll just let R go to infinity. So if I let R go to infinity, this is going to be something plus infinity. So that's infinity. The square root of infinity is infinity. And something divided by infinity is 0. And yes, I'm trolling a little bit. You should do this as a rigorous limiting argument. But you get the point. So I'm sorry. That should do. So I'm sorry. That should be a minus sign there. But anyway, this all turns to 0. And so we are left with E equals eta over 2 epsilon naught. We will get this result by a much simpler means later when we learn about Gauss's law, but it will be nice to find out that our theory of electricity and magnetism is internally consistent, and we can get the same answer two different ways. But when we do Gauss's law, you'll find we can do it a lot faster. Alrighty, so in the next video, we will continue our explorations of electric fields. Have a good one.